uh, to all those who are listening to this. So here I'd like to introduce some basic notions and the way we approach discrete optimal control. I will not be exhaustive, but I'll introduce you to some facets of this theory. The foundation of my lecture is a paper by Boltiansky, which I will maybe should I? Okay, I'll show it slightly later, but first let's get started with some preliminaries. I have recorded these three lectures of modules of 15 to 20 minutes each, and I'll play them one after the other, and I may sort of add my comments along the way. Please let me know if the audio and video are clear. All right, let's look at some basics of discrete time optimal control. Okay, the nice aspect of discrete time optimal control is that you're invariably dealing with, you're always dealing with algebraic equations. You're no longer dealing with differential equations. Algebraic equations. And let's say if to start with, you have an underlying state space model. So you have something of the form xi plus 1 equals fxi ui. So let's even make this stage dependent. That's fine, the f dynamics. So xi could belong to some subset m of Rn. Uh, ui could belong, so m, let's call this mi. ui could belong to certain set of Rm, and fi could be a mapping from mi cross ui to Rn, and you could have smoothness and other related properties. Okay, all right. So now let's realize the first sort of trick or manipulation that we can perform on this equation here, which is as following. So I can write that equation as the following. Uh, Equality, right? I can write this in this form. Now, if I were to look at this equality, I can look at it as um, as sort of a level set in Rn cross Rn cross Rm, right? Why? Because I have this in Rn, this in Rn, and this in Rm, right? So if I were to consider a Euclidean space of this nature, so this constraint here is of the form of some level set, since we are concerning ourselves with smooth functions. So this here is of the form xi plus 1 minus fi xi ui equals 0. I'll just pause it for a minute. Are there any questions here? What I'm trying to motivate is the fact that in discrete optimal control, okay, let's first, you're taking dynamics of a system, but those dynamics are in discrete form. So discrete form means they're algebraic equations. Maybe they are in N, in this case, the state space is in Rn, the controls are in Rm, and there is xi plus one, which brings in another Rn. And then this is an equality constraint, right? So this is assuming smoothness of the Fi map, etc. It's like a level set. What is a level set? It's all, in this case, where I have frozen the video. It's all xi plus one, xi's and ui's, which satisfy this equality.
All right. Now, this is describing something which we know as system dynamics. Now, in addition to that, what do we have in an optimal control problem? You have some initial state. So so x0 is some um, specified state. So let's call that x0 equals what should we say? Okay, let's say a, and x at some stage n equals b. So you have stages 0, 1 through n, and therefore you apply control u0, u1 through un minus 1, right? And in addition to these, you have a performance measure. So you have a performance measure I equals 0 to n minus 1, say ci xi plus you have something at the final time, right? So this is your measure of performance. So let's write these things down. So you have a state evolution description, you have initial conditions, final conditions, you have a measure of performance, then you will have constraints. So what will these constraints look like? So these constraints will be like ui at every stage belongs to some set ui. So this is true from I equals 0 to n minus 1. Then xi at any stage maybe belongs to some set chi I.
Just a pause. Places I've used chi for the state belonging to that set. At places I've used mi. I apologize for this inconsistent notation, but please bear that. Keep that in mind.
Again, I equals 0 to n, right? Okay. Now, what we do in the way we okay, so this is number 4. Let's label this as the fourth. So that's the constraints, right? Okay. So now we have
Also, bear in mind that the type of constraints I'm considering is at each stage. Say ui belongs to the capital UI set and xi, the state belongs to the capital chi set. So they would incorporate notions that you've seen like inequality constraints or control bounds. Everything is accounted for here.
the problem specified. So now it's just that we say um, you want to minimize this with respect to the control actions, right? You want to choose these to minimize this cost function. All right. So, um, so one of the ways you go about this, I mean, so let's look at um, uh, so let's look at the overall picture here. So now you have a state space which at each point, so let's name the stages as, so you have Rn cross Rn cross Rn. So this is at stage 0, 1, and till n.
So this is the horizon over which you're considering the optimal control problem. You're starting at 0, so discrete n plus 1 stages, you'll apply n controls.
Then correspondingly, you have the controls. So at stage 0, m till n. So this, let's call this. This is n minus 1, right? Okay. Okay. So now if I decide to look at the optimal control problem just in terms of such level sets like I have done here. So what I will do is concatenate these variables. So I'll have x naught, x1 through xn.
Please note at each of the stages, like x naught belongs to r small n, x1 belongs to small rn. So now you are having a state space of capital N plus 1 into small n.
Right? And at each, so this is now a n into n plus 1 state. Then I do the same for the control. Then u naught through u n minus 1. So then I have an m into n. So what I do now is, so now I'm going to enlarge my state space. I'm going to call it A equals n plus 1 plus mn. So this is the dimension of my new state space. So I'm going to look at everything in RA. Now, when I look at everything in this new state space that I have, right, I also need to look at constraints. So for instance, so if we know that u naught, u1, un minus 1 belongs to some constraint set. So let's say u naught cross u1 and so on to un minus 1, right? And further, I also have state related constraints. So x naught, x1, and so on till xn belongs to chi naught cross chi1 and so on till chi n, right? Okay. Now, therefore, this whole issue of finding an optimal control law. So an optimal control law is basically the string. This is what we want to find. So just to recap things, let's start from the beginning. Okay. We begin with algebraic equations. So this the dynamics, right? With some smoothness assumptions on these functions, right? And the state belonging to some subset mi. Oh, I think I later changed this mi to chi I, so maybe I'll make that change. And then the controls belonging to some set. So as I said, this dynamics can be looked at in terms of this type of an equation, right? In which operates in a level set in this Euclidean space. Then you have initial and final conditions. Well, this not be specified. I mean, I'm just taking a particular example. It could just be free as well. And then you have a cost function. Then you have constraints on the control and states. And you may have mixed control state constraints as well. So you could have some things like this. Cxiui equals 0 at any particular stage. So then the way we proceed with finding the optimal solution is we augment the entire state sequence over the n stages this way, right? And work in an larger dimensional space. And then in simple terms, then what happens is you have you have some level set which is corresponds to the state dynamics. Then you have another control set, control constraints. Then further, you have something which are so state constraints, etc. So now what you need to look at is the intersection of these states. So the intersection of this and this will give you the admissible region where you want to find your minimum. It is minimum of the cost function. That is, you wish to work on that u naught to un minus.
Notice one of the things. What are we trying to do? We are converting a dynamic optimization problem into a static optimization problem. We've sort of swallowed in all the states over the n stages, the control over the n stages, and then we are looking at an intersection in a larger state space, and then deciding on what the optimum is, which is like a static problem in the larger state space. But then we have to, from that static optimization problem, get our recursions and older ideas of Hamiltonian maximization and things like that.
One which yields the least value of your cost function. So now when you come to something like here, suppose you say that this is the optimal value of your uh, control at a particular stage. So let me see, how do I say that? So let's say, mm, okay, let me see, how do you can say that as saying, yes, suppose this was at stage I, and then you perturb the control. So you had an optimal value of the control, and then you perturb the control as ui star plus delta ui. The question is, would the cost decrease or increase? So if the cost decrease, then you this ui star is not the optimal control. So basically what you need to find out is when you perturb the control, does this cost um, become greater than equal to CUI star? Now this would be true for all delta UI such that UI star plus delta UI is in the permissible set. So all right, so let's take a break here. I will continue with after refining a few of my thoughts.
Okay, are there any questions so far?
Professor Banawar, this is
Yes,
Mangal.
yes, please.
Um, so the formulation what you so far is looking, because it looks like when we are doing this direct method, right?
It is not entirely true. In direct method, you just set up all these things and leave it to some optimization solver. But here I'm not going to do that. I'm going to bring in the notion of necessary conditions. Just like in the continuous time case, you brought in the necessary conditions in terms of all those Hamiltonian maximizations and Lagrange multipliers, etc.
Mm.
I'll bring in similar conditions now.
Mm.
If you had left the problem at this stage, you're correct in the sense if I just formulated like this and fed it to a solver saying, okay, this is a nonlinear programming
Mm.
solver,
Mm.
you take these variables, I agree. But no, I will go a stage further. I will get necessary conditions now and then use those necessary conditions to yield a 2-point boundary value problem like this.
So,
Am I clear?
so like for this will be like again, but you will be using Lagrangian, right?
Yes, Lagrange multiplier, not Lagrangian.
Lagrangian multiplier. So that, but that will be you. But okay, you have inequality constraint also, right? That also, or no? That is a on the bound. It will be. I think anyway. In next video, it would be clear, right?
Sure. Just hold on.
Okay.
And I just wait till the end, then you'll get a flavor of it, though I'm afraid I won't be able to convey everything, but let's see how much you get.
Yeah. Okay. Okay.
Shall I start with the next
Yeah.
one?
Yeah.
So let's in this class of constraints that we have, if you recall, we specified that each of the state at each stage has to belong to some set. I had earlier called it M naught, M1, so on, and then I changed it to chi naught, chi 1. This also incorporates inequality constraints of this form. So if you look at this constraint, you have a surface which is Jx equals 0, and on either side of it, so this side is maybe Jx is less than 0, and the other side you have Gx greater than 0. So when you have something like this, your region becomes this whole part. This is your region now, right? And that's the equivalent of your chi or m, whatever you take. Now let's shift to the formal slides now that we have a preliminary idea of how things are in discrete optimal control. So everything is discrete optimization and it's the intersection of surfaces as I have shown. So let me go to so now comes the important part, which is
Okay, Mangal, just to tell you, see, now you will see where if you look at the continuous time optimal control problem, many of the conditions come from some linear approximations. I mean, because so many of the conditions are local conditions, right? So now you'll see, irrespective of the type of sets considered in terms of your state, where should the state lie, whether it comes from inequality constraints or equality constraints, or where the control lies. Now is where this is the point where Boltiansky makes this brings in this construction called a tent, which is like a tangent convex cone. And to this approximation of this set at that candidate optimal point, he, based on this, he constructs necessary conditions.
When you have these sets, for instance, in this case, uh, let's um, let's look at okay, and let me get um, yes, let's look at this this set. This is your, let's say this was your constraint set, and then if it so happened that this was the point which you were considering as an extremum of the performance measure, then in order to approximate this set, you use this K, which is the tent corresponding to that set. Now, the difference between, okay, now in this second case, so this is for an equality constraint. So the omega here, so this arises out of an equality constraint, something like h of x equals 0. So that's like a surface, right? And then what is meant by a tent is basically something which is like a linear approximation to this surface close to that point. So that is this K, right? Similarly here, the set is now this whole omega. Now, and the point you're considering is x naught, right? Now, close to x naught, the closest linear approximation is this bluish green shaded surface, right? So these become the approximation. So they are called the um, uh, tangent convex cone approximations to these sort of level sets or surfaces or any other type of sets close to the point of which is being considered for optimality, right? Okay. So A is tent for an equality constraint and B is the tent for an inequality constraint. So
Mangal, at this point, we are just giving an intuition of what these tents are. There is a formal definition of the tent, which Boltiansky gives in his paper, and I'll show in a subsequent slide.
Okay, thanks.
maybe I'll get rid of some of these here. Okay, all right. So let's go through the formal. No, let's maybe, since we've seen the earlier parts, let's come to, yes, let's come to the problem we are interested in solving. So, as mentioned before, we are interested in solving a problem of
So I'm sort of jumping a little bit here, but you'll see things soon.
this form, right? With the state dynamics, state belonging to a certain set at each stage, control belonging to a certain set, initial conditions specified. So as I mentioned before, we stack all the variables together and perform a minimization over the concatenated vector. Recall I had told you, and I also had said that the whole state space now becomes the string of such variables. All right. Now, so what this does is it removes all these discrete recursions and converts the entire problem to a static optimization problem in terms of Z. So that's the way the methodology to find the optimal control law works, and that can be cast in the familiar form that we see in continuous time in terms of a Hamiltonian maximization, in terms of the co-state, etc. We'll see how this is done. So first and foremost, let's look at this concatenation, right? Okay, so this is your cost. Fine. Now we define something for this at each stage t, right? And this, remember, 1 through small n is the number of states. These are the stages. So let's have that very clear. So you have stages 0, 1, n minus 1, n. But at each of these stages, you have an n state vector. N state vector, and you have uh, m number of controls. Remember? Okay, I think that's set somewhere right. Okay, so this is the state dynamics. Then what do? We convert these state dynamics to constraints of this form. This is nothing but saying xit plus 1 equals fi xt. So this is the converting the state dynamics to constraint sets. So this is number 3. So then in the overall big picture, remember omega t, which has, so now we consider the state constraint at each stage. So only this, the rest of it, notice in this concatenation, see, this is the concatenation of, let's remember what Z is. Z is this, right? So now if you look at number 4, you have all all these are in Rn except one, which is the t plus 1th.
So here is where you have to see how things get sort of isolated based on the stage you're in. So, and this is where we will start constructing. So if you look at the itemized dots 4 and 5, so each of those sets, you have one particular stage, and at that particular stage, when you are considering something optimal, you are going to consider an approximation, a linear approximation of that, which is called a tent.
Factor that is basically at the t plus 1 stage, and these are all your controls through all your, so this is Rm cross Rm n times, right? So it goes 0 to n minus 1. So I hope that is clear. So you're considering now, see, because now all the constraints have to be considered in the larger picture. So in the larger picture, you have MT to be the constraint at stage T, right? Okay. Similarly, you can do it for the control. So this is for the control, right? So considering the control state constraints at each stage. Remember, we are considering this at each stage, right? So, which is why you see just this coming into the picture. All right. So maybe let's get rid of this. Okay. All right. Now, okay, we have converted everything to the form we would like it to be in. Now we rewrite the optimization problem. The optimization.
So Mangal, if you did it your way, you would have just fed it to the nonlinear programming solver at this stage, saying all these are done. But we go ahead.
Problem is now rewritten in terms of the larger state space, right? So we have minimized this subject to this, right? What is this? FTZ, which is this, number 3, right? Now, in addition to that, so okay, we have the state dynamics, right? For I denoting the number of states, so I think that's I equals 1 to small n, I think. Yes, this is not correct. This is small n. It's a number of states, and then it's over the stages. Now you have the state constraints and the control constraints, right? So it is, notice, it's the intersection of all these points because a candidate optimal should satisfy the state constraints, the control constraints, and the state dynamics, right? That's the idea. So now with this, we something which satisfies this and it is an optimizer, then we go about giving our conditions. And when we do that, we need to construct tents. Qt is a tent, local tent to ut at that point. Similarly, kt is a local tent to empty. Remember the state constraint at the uh, candidate optimal state, right? And this happens for each of those stages. So this is how the entire problem has been converted to just a static optimization problem. This is now a static optimization problem because you have frozen this in this form. Okay, all right. So, all right. So now we go ahead and construct tents. So this part is, remember, we have talked of Qt and KT being the tents. So now we are replacing um, the earlier sets with the
So what you're doing is, in fact, if you see the second itemized dot and you see the KT with the curly bracket upstairs, now it's a local tent for the earlier set. So it's like a linear approximation. And the other all multiples of Rn and Rm raised to n are the copies of all the other variables.
equivalent tents at that. So these are tents, right? And then when you take this again, this entire string again, as you took the omega t gets converted to k to a new notation, kt bar and qt bar, right? And soon after this, we will, I need to take a pause. I'm sorry, I have a call.
Just a second. And all right, any questions so far, please? Okay, let me just go to that.
All right, so let's proceed. So we start constructing these tents, these tangent convex cones, um, and all this is basically following that procedure, but just keep in mind the following facts. So for instance, when you look at something like this here, the superscript means a particular uh, state which is propagating. So I, if you remember, goes from 1 through n, and the subscript t goes from 0 to n, right? So for instance, in the in this relationship here, what is being said is nabla calligraphic F I T. So this means you have Fi. Oh, sorry, just 1 second. So you have F, yes, F1 by, uh, just, yes, yes. So you have this, the first one would mean this by Z1 and so on till this Fi is, yes, Fit of Zn, right? And that inner product Z prime minus Z star, right? And this is a scalar multiple, which belongs to the real numbers. Now, if you look at these tens which are being indicated for uh, each of these, if this is a tent at a particular stage, so this is at a particular stage, and then you have the overall local tent in the global picture. So you take an individual tent at that particular stage and then you perform and you concatenate it to get an overall tent. Some of these are better understood when you look at the paper, and please remember the A here is the combined dimension of the state space, which we had, I think, mentioned here. Yes, this was mentioned here. And so okay, so just this last itemized dot, take a look at that. So these Q naughts through Qn minus ones and K naughts through Kn are not separable in Ra. Therefore, these Q naughts through Qn minus one is also not separable, and you can look at details for this. And then we come down to applying the necessary conditions. Now, this is all based on theorem 2.15. So I think what I'll do instead of going through these, so how do these go? You have the necessary conditions here, then you have a simplification of the dynamics, and then you have the control and
I really don't expect you to follow these 3, 4 slides, but I'm just sort of going through them just for you to get a flavor. And later, when I share these slides separately with Mangal, please take a look at them.
all those 3 slides lead up to the Hamiltonian formulation. So now you're coming back to terminology that you had seen in the continuous time version of the maximum principle. So this is how the Hamiltonian gets built up. So before we come to the slide, so just let's go back and look at the main theorems given in Boltiansky. Okay, so this is theorem 18. Okay, let's go to
So
16.
please note the theorems from the paper by Boltiansky have been given, so you can easily go back and refer to them.
17 and 18 from the main paper, which we call here as 2.1.14, 2.15, and 2.16. So let's look at 2.14. So omega 1 through omega k are sets in Rn, and Frn to R is the function to be optimized. Therefore, you are looking at the optimization domain as this. And let's say this is your X star is your candidate optimal, right? And further, now let Ki be the local tanh of omega I at X star for each of the indices running up to K. Now for F to attain its minimum relative to this subset sigma at X star, it is necessary that there exists these elements in the dual cone. I think I have explained the dual cone in the process of these lectures. I don't recall my first two lectures whether I covered dual cones, but if I have not,
This is, I don't think I sort of have not covered dual cones anytime because I think I mistook this for something else. So I'll shortly explain. If you look at the Boltzmann maximum principle, so it relies on this notion of a tent, which is a linear approximation to a set near a candidate optimal. Second is this notion of a dual cone, which I will shortly explain now.
I think I should just quickly go back. We are on slide 20. So let me just quickly go to a dual cone.
Okay, in these two figures, take the one on the left-hand side. So you can see K, the green one, and K plus, the sort of the bluish green one, bluish greenish. So K plus is the dual cone of K. Both, see, K is a convex cone to start with. It's a cone at the point x naught, the vertex of the cone. It's very important to specify the vertex of a cone. And what is a cone? A cone is a set in Euclidean space, basically Rn, where if x is a member of the cone, alpha x is also a member of the cone for all alpha greater than equal to 0, right? So now this is a cone at x naught. Therefore, those vectors are shown with subtracting x naught. If you look at that vector x minus x naught, right? So let's see.
Okay, yes, convex geometry. Right, let's just quickly go through this definition. The dual cone here, I'm here. So the dual cone K superscript plus at x naught for the cone Kx naught. So Kx naught is a cone with a vertex at x naught is defined as all those points in Rn, such that, okay, this is A minus, please note this, A minus x naught, inner product x minus x naught is greater than equal to 0. For this should be true for every x in the cone. So let's look at how this looks like. So here is your,
See, an easy way to understand dual cone is if you draw a vector from x naught, that vector should make an acute angle with every other vector which lies in K. Such vectors are permissible. So that's basically the meaning of the dual cone.
what is shown in green. So let me erase some of these and then. So what is shown in green is your convex cone, and then the elements in this K plus belong to the dual cone. Why is that? Because if you look, okay, if this is some global origin and you have this as x and this as x naught, x and x naught, so this is x naught where the vertex of the cone is. So these vectors here are a minus x naught, and this is x minus x naught, right? Now, if you see a minus x naught, we are claiming that a is in the dual cone. If that's in the dual cone, it should satisfy this relationship for every x in kx naught. In fact, that would be true for these points. The main idea being that, so if you see these lines here make a 90 degrees with this edge of the cone and this edge of the cone, right? Okay, so that's the notion of points in the dual cone. So let's not worry about separability right now. Okay, Then the supporting cone is defined as the closure. So I won't get into too many details of this. And um, so we will jump to the main theorem. So you have associated with these convex cones a notion called a dual cone. Yes, so now we will come to theorem 2.14. So we've been going through that, and these are the elements in the dual cone. Now, satisfying, so these are necessary conditions. Please remember, we are getting, so we need psi naught less than equal to 0, such that you satisfy this. And if psi naught is 0, at least one of these vectors should be non-zero. One of these vectors sitting in Rn, right? Okay, so this is all in this. Remember, in our problem now, we have concatenated the entire state space, so we have made it into a larger entity.
You may be wondering, why am I showing these three theorems? The first theorem actually doesn't bring in any other constraints. It's a basic optimization over certain sets, convex sets, omega 1 through omega k. I think these are all they assume convex. I think in this, maybe not. They're not even assumed convex here. Then the second one actually has some constraints of in addition to these sets, so they come in from the control aspect. Now the third one explicitly has the type of constraints that we see in control.
But these are essential theorems for basic minimization of functions with constraints, right? All right. Constructing these local tens. So what is the extension of the next theorem over the previous one? Now, if you look at this, now in addition to the omegas, you have the thetas coming in here, right? And now your set is sort of got large, more restricted. It's an intersection not only of the omegas, it's also an intersection of that with the thetas, right? Um, and now the thetas, I think there's a condition on the thetas that they are not separable. Yes, the thetas are not separable, the theta 1, theta naught through theta L, and the cones corresponding to the thetas are the Q, or the tents corresponding to them, the local tent.
So maybe there are a few words here which I have not explained. There's the separability of convex sets. So you would have to go through the slides to understand what I mean. In a sense, in the continuous time, I had given a brief explanation of it.
Are these. F is the function to be minimized, then you need the existence of these vectors in the dual cone. Again, this is true, but then look at the difference here because of the fact that these QIs arise from non-separable sets, right? And therefore, this earlier condition becomes like this, where the delta x is all elements from x. So x star plus delta x should belong to the intersection of the QIs. Now going on from here to the final one, 2.16. So what do we have here? Here we explicitly introduce initially the convex sets, which you have the omegas, the equality constraints, the inequality constraints. So these are the equality constraints. These are the inequality constraints, right? And we've given them indices of NEQ and NIQ. So now, if X star is a minimizer of F, right? What are the conditions? So now the conditions here, I'm not going through the entire math again. So uh, the multipliers are given as, oh yeah, the multipliers, these are the multipliers, equality constraints and inequality constraints. And you have this condition, and further you have one more condition because of the inequality constraints, where the multipliers corresponding to the inequality constraints are less than equal to 0, and you have to satisfy this condition. So if you are at the boundary, this is 0, fj is becomes 0, therefore eta is not determined, becomes 0. All right. Okay. So these, so how do we get into the framework of Hamilton?
So, Mangal, here's one more aspect. The answer or part of an answer to your question is here is where you can see all those Lagrange multipliers multiplying all the gradients of those equality and inequality constraints.
Yeah.
Hamiltonians and Hamiltonian maximization, given what we have here. Um, cannot go much into the details, so we've done all this. So this is all in the larger state space. What happens is that now, based on those conditions that you had, you can define a Hamiltonian as you have here at each stage t, and then you can talk of multipliers, and depending on how these tents are, you can talk of a constraint of this form. Now, this will become a sort of a maximization constraint if you're talking of the control coming from convex sets, and then you massage this Hamiltonian into getting what is your final discrete time Pontryagin maximum principle, and this is what it is. Um, you must excuse me if I have not gone through it too much detail, but I essentially wanted to convey the concept of all these equality constraints, inequality constraints, the tangent convex cones, which are called tents, and then how the optimization algorithm proceeds. All right. If you have any queries, please get back to me. I'll be happy to answer them.
So, Mangal, after this talk, I'll send you this set of slides separately, and I'll also send you the paper. But the reference, if I give you, you may be able to get it by Boltiansky, on which this entire talk is based.
Uh, Thank you.
Let me just, should I stop sharing my screen? I'll stop. Okay, fine.